Welcome to our video lecture on mole ratios. Our objectives for today, we're going to define stoichiometry, we're going to describe the information that we can get from balanced equations, we're going to define mole ratios, then we're going to use those mole ratios to carry out some stoichiometric calculations. Calculations means you definitely want to have your handy-dandy calculator nearby. Periodic tables also super helpful. If you don't have one of these, pause the video, grab them both, and here we go. So stoichiometry is simply the math of chemical reactions. Just like recipes are the maths of baking and cooking, we can take our ingredients, we have quantities of ingredients, and that's going to give us quantities of products. We're going to do the same thing with our balanced chemical equations. And just like with our recipes, we can scale things up or down. This particular recipe makes 4 dozen cookies. If I wanted 8 dozen cookies, then I could just scale all of my ingredients up to figure out everything that I needed to make those 8 dozen cookies. We can do the same thing with balanced equations, which is exactly what we're going to do today. So again, stoichiometry is the math of chemical equations. We're going to look at all the stuff that we can learn from a balanced equation. These are all the things that we can learn from balanced chemical equations. So here's our example of a balanced chemical equation. I have my invisible 1 nitrogen gas and 3 hydrogen gas molecules and 2 ammonia molecules. I can figure out particles from this balanced equation. I can figure out how many atoms of nitrogen, how many molecules. I can use that molecule number and scale up. Maybe I didn't want 1 molecule, I wanted 10. I can multiply everything by 10, so 10 and 30 and 20. Or I can multiply everything up by 6.02 times 10 to the 23rd power and have 1 times that and 3 times that and 2 times that. Remember that this is our mole number, which means that I can have 1 mole of nitrogen or 3 moles of hydrogen, 2 moles of ammonia. This allows us to use our balanced equation not just for molecules but also for moles, and that's what we're going to do a lot of today. We can also use those moles to find masses, and we can use our moles to find volume. Remember that volume of a mole at STP is 22.4 liters per mole. Lots of information can be found just by looking at these coefficients in our balanced chemical equations. So let's practice a little bit thinking about these balanced chemical equations. So hydrogen sulfide, or H2S, is found in volcanoes, which is kind of cool. And here's our balanced equation. This can tell me that I have 2 molecules of that hydrogen sulfide and 3 molecules of oxygen gas can react with that to make 2 molecules of SO2 and 2 molecules of H2O, because these balanced equations are showing me those coefficients. But I can also think about it in terms of moles. And again, this is what our focus is going to be today. 2 moles of this and 3 moles of this can react to make 2 moles of this product and also 2 moles of this product. And these mole numbers are going to be super important for us today. Just like we can scale up our recipe, we can scale up our balanced equations. I could write some ratios for ingredients in this recipe. For every 1 cup of butter, I need 2 eggs. So for 1 cup of butter, I need 2 eggs. That will allow me to scale up and down my recipe. Maybe I only have half a cup of butter in my fridge right now, and so I can scale down my recipe. 2 eggs for 1 cup of butter, but I only have half a cup of butter. That means I can only use 1 egg in my recipe. We can make the same kinds of ratios using our balanced equations. So again, if you don't have a 1, we're going to assume there's an invisible 1 in that equation, right? So you've got 1 nitrogen and 3 hydrogens makes 2 ammonias, and H3 is also known as ammonia. So I can make a ratio of how much nitrogen to how much hydrogen. I know that there's 1 mole of nitrogen for every 3 moles of hydrogen. I can also make a ratio for nitrogen to ammonia. For every 1 mole of nitrogen, I can produce 2 moles of ammonia. I can do the same thing with hydrogen and ammonia. For every 3 moles of hydrogen gas, we can make those 2 moles of ammonia. I can also take the reciprocal of any of these, and instead of saying 1 mole of nitrogen to 3 moles of hydrogen, we could do 3 moles of hydrogen to 1 mole of nitrogen, and all we're doing is making these ratios, these fractions, showing the different pieces and parts of my equation and their coefficients. So those coefficients in the balanced equation are super, super important. And this is why. So again, we're going to throw that invisible 1, make it visible in front of that N2. How many moles of ammonia are produced? 1.5 moles of nitrogen react with hydrogen gas. So what I'm going to do is think about if I have 1 nitrogen makes 2 ammonias. So my ratio is 1 to 2. Well, now I only have 0.5 moles of nitrogen. So I only have 0.5. Whoa, that's not a 5. I only have 0.5 moles of nitrogen. So if 1 mole makes 2 moles, 0.5 moles is going to make half of that, right? So only 1 mole of nitrogen, 1 mole of nitrogen trihydride or ammonia. I can do this math in a railroad track. So I can take 0.5 moles of nitrogen as my given, and I want to find out how many moles of ammonia there are. So I'm going to put nitrogen on the bottom because I want to get nitrogen to cancel out. I'm going to put ammonia on the top because I want to find ammonia. That's what my question is looking for. And then the numbers that I'm going to put in front of these guys are the coefficients from the balanced equation. So I'm going to go up and I'm going to find that 1 in front of nitrogen, that 2 in front of ammonia. And then I'm going to, just like we do with our other pieces of dimensional analysis, cancel out tops and bottoms. N2 cancels out top and bottom. I'm left with NH3, which is good because ammonia is what I'm looking for. So now calculation-wise, 0.5 times 2 divided by 1 is going to equal 1. 1 mole of ammonia. And that's what we had predicted when we did the math in our heads. Let's do this one. How many moles of nitrogen will react with 7 whole moles of hydrogen gas? So I'm going to start with this 7 moles of hydrogen gas. That's going to be my given. This is my given. My wanted is moles of nitrogen. So I want to figure out how many moles of nitrogen will react. I'm given hydrogen. I want hydrogen to go away. I'm going to put it on the bottom. I want to find nitrogen. I'm going to put it on the top. So now I'm going to go back up to that balanced equation, and I see 1 in front of nitrogen. I'm going to put a 1 in front of nitrogen. And I see a 3 in front of hydrogen. I'm going to put a 3 in front of hydrogen. What cancels out top and bottom? Hydrogen. H2, H2 cancels out top and bottom. So now I'm going to do 7 times 1 divided by 3. 7 times 1 divided by 3, 7/3, or we could say 2.3. And our unit label, I still have moles, but instead of moles of hydrogen, because hydrogen canceled out, I have moles of nitrogen gas. 7/3 of a mole, or 2 1/3 moles of nitrogen gas will react with those 7 moles of hydrogen gas. We're going to do these couple problems together. The next slide will be yours to do on your own here in Edpuzzle. So step number 1, always, always, always make sure that your equation is balanced. So let's go ahead and balance this equation. I've only got 1 oxygen here in the products, and I've got 2 atoms of oxygen here in the reactants. So I'm going to put a coefficient of 2 in front of the water. But now I have 4 hydrogen atoms, and I only have 2 hydrogen atoms. I'm going to put a 2 in front of my hydrogen. I now have a balanced equation. I'm going to go ahead and throw a 1, that visible, invisible 1, in front of the oxygen gas. Let's look at a problem. How many moles of oxygen gas are needed to produce 1.4 moles of water? 1.4 moles of water is my given. This is the information that I'm given to start with. What I want to find my wanted is moles of oxygen. So we always start our railroad tracks with the given. 1.4 moles of water. I want to get rid of water and turn my water into oxygen. I've got water on the top. I'm going to put water on the bottom. I want to flip my water into oxygen. I'm going to put oxygen on the top. I'm going to use the numbers, the coefficients from my balanced equation in order to do these calculations. So I've got H2O. I've got a 2 in front of my H2O. I'm going to put a 2 there. I have a 1 in front of O2. I'm going to put a 1 here. So now top and bottom, H2O cancels out. Boom, boom, and we're left with 1.4 times 1 divided by 2. And so our answer is going to be 0.70. Unit label, I still have moles of oxygen. is going to be our answer. And this makes sense because I've got a 1:2 ratio of oxygen to water. And so I'm going to have half as much oxygen as I have water. It makes sense. Let's do this one together. And then again, the next page is yours. How many moles of hydrogen gas are needed to react with 0.3 moles of oxygen gas? 0.3 moles of oxygen gas. This is our given. Moles of hydrogen gas, this is what we want to find. This is our wanted. We always start our railroad tracks with the given. 0.3 moles of oxygen gas. And I want to flip my oxygen gas into hydrogen gas. I've got oxygen gas on the top. I want it to go away. I'm going to put it on the bottom. I want to flip my oxygen into hydrogen. I'm going to put my hydrogen on the top. What numbers do I need to put in front of hydrogen and oxygen? We're going to go back to our balanced equation. I see in front of H2, I've got a 2. In front of O2, I've got a 1. And so now oxygen top and bottom cancels out. Calculation-wise, I'm going to do 0.3 times 2 divided by 1. And that's going to give me 0.6. My unit label, I still have moles, but instead of oxygen, now I have hydrogen gas. And so our answer is going to be 0.6 moles of hydrogen gas. How many moles of hydrogen do I need to react with those 0.3 moles of oxygen? I need 0.6. This makes sense because we have, again, a 1:2 ratio oxygen to hydrogen. I need twice as much hydrogen as I have oxygen. And so if I've got 0.3 moles of oxygen, I need twice as much, 1:2 ratio, 0.6 moles of hydrogen gas. Good? Good. These ones are yours to do in the Ed puzzle. Remember to always start with your given. I'm going to give you a hint. Here's our given, and then find the wanted. Here's your wanted for this first problem. Get ready, get set, go. So we started with that given, 6.0 moles of oxygen gas, 6 moles of oxygen gas. We're going to flip it into moles of water. I'm going to put oxygen on the bottom, water on the top. I have a 2 in front of water. I have invisible 1 in front of oxygen. 6 times 2 divided by 1 is 12. Unit labels, oxygen top and bottom cancels out. And so we are left with moles of water is our final answer. And then this one, how many moles of hydrogen gas we needed to produce 10 moles. Ooh, that shouldn't say produce. That should be react with, because we're not producing oxygen. React with 10 moles of oxygen gas. Here's our given 10 moles of oxygen. How many moles of hydrogen gas? I'm going to flip my oxygen into hydrogen. Back to our balanced equation, I see a 2 in front of H2, that invisible 1 in front of oxygen. Oxygen top and bottom cancels out. Calculation-wise, 10 times 2 divided by 1 is going to give us 20 unit label moles of hydrogen gas. Is our answer. All right, so we're going to do another problem. 56 grams of nitrogen gas reacts with excess hydrogen. So we're going to take a quick minute and talk about what even does this word excess mean. It just means extra. It means don't worry about running out. It means that we can take all of that nitrogen and react it to make ammonia in this reaction. It's kind of like if you're building cars and you've got all these car bodies and all these tires. You can build complete cars from all those tires and then have some tires left over. So tires would be in excess, they would be extra. In this problem, I can use up all of my nitrogen. I'll have hydrogen left over. So you might be thinking, easy peasy, we're going to do 56 grams of nitrogen, put nitrogen on the bottom, put ammonia on the top. I'm going to do a 1 and a 2, and voila, final answer, except my friends, these mole ratios are mole ratios, not gram ratios, which means that you cannot start with a gram and then use your mole ratios. You need moles to use your mole ratios. So what we have to do first is convert our grams into moles, and then we can do exactly what I was about to do. So 56 grams of nitrogen. We're going to convert our grams of nitrogen into moles of nitrogen. How do I do that? We go to our handy dandy periodic table. So I have N2, nitrogen's mass is 14.007, but it's N2, so I'm going to double that, and I'm going to put 28.014 grams on the bottom, 1 mole on the top. Because I have grams on top, I want grams to go away, so I put grams on the bottom. So now I'm going to use my handy dandy calculator to figure out how many moles of nitrogen I have. So 56 times 1 divided by 28.014 gives us a grand total of 1.999, lots of digits. I'm going to round that to 2.0 moles of nitrogen gas. Now that I have moles of nitrogen gas, I can use my mole ratios. So now I'm going to do 2.0 moles of nitrogen gas. I want nitrogen to go away. I want to flip my nitrogen into ammonia. I'm going to put nitrogen on the bottom, put ammonia on the top. Now I'm going to use those coefficients from my balanced equation. I have invisible 1 in front of the nitrogen gas. I have a 2 in front of ammonia. What cancels out top and bottom? Nitrogen cancels out top and bottom. And so now I can do 2 times 2 divided by 1 equals 4. I have 4 unit label left, moles of ammonia, Yay, except we're not done because the question is asking for mass, not moles. So I'm going to take this answer, 4.0 moles of ammonia. We're going to get rid of moles by putting moles on the bottom. We're going to flip our moles into grams. How many grams in 1 mole of ammonia? Back to our periodic table. So ammonia is NH3, so I need 1 nitrogen, 14.007 plus 3 hydrogens. Hydrogen is 1.008. So 14.007 plus 3 times 1.008 gives us a grand total of 17.031. 17.031 grams per mole when I'm talking about ammonia. So now moles top and bottom cancel out. We're left with grams of ammonia, which is exactly what our question is asking us to find. So now back to the calculator. 4 times 17.031 divided by 1 gives us something. I pushed wrong buttons on my calculator. Trying again. 4 times 17.031 gives us 68.124. Sig fig check. I get to keep 1, 2. I get to keep 1, 2 sig figs. So I'm going to keep 1, 2. That 1 is going to leave that 8 and 8. And so my final answer is 68 unit label grams of ammonia. I can make 68 grams of ammonia if I have 56 grams of nitrogen gas. So this map kind of helps us keep in mind that we have to always convert to moles first. So we're using G for the given. This is what we're given in the question. W's are wanted, what we're trying to find. Whatever it is that we're starting with, mass, like we did in that previous question with grams of given, or we might have how many atoms or molecules, or we might have volume in liters. Regardless of what you start with, we've always got to convert to moles first. Once you convert to moles of your given, then you can use your mole ratio. These are just the coefficients from your balanced equation, moles ratios, coefficients from the balanced equation to turn your givens into your wanteds. And then once we have the wanteds in moles, we can convert those moles to either grams or atoms or molecules or volume in liters. So let's practice. Here we go. 12 grams of hydrogen gas react with excess nitrogen gas. That just means that we have extra. Don't worry about running out. What mass of ammonia is produced? So we're going to start with our given. 12 grams of hydrogen gas. We're going to convert our grams into moles because we always have to go to moles first. How do we do that? I've got grams on top, put grams on bottom, turn my grams into moles. Once you've got those moles of hydrogen gas, then we can go ahead and flip into ammonia. is I've got hydrogen on the top, put hydrogen on the bottom, turn my hydrogen into ammonia. Remember that we're going to use our coefficients from the balanced equation to do this. So think about what numbers need to go here and here. And then, now that we've got those moles of ammonia because hydrogen canceled out, now we're going to go back from moles to mass of ammonia. So I've got moles on top. I want moles to go away. I'm going to put moles on the bottom. I'm going to turn my moles back into grams. But this time I'm looking at how many grams in 1 mole of ammonia. So think about what is the mass of NH3, how many grams per 1 mole. I'm going to have you finish this one in Edpuzzle. All right, so it was 12 grams of hydrogen gas. We decided that we were going to turn our grams into moles, 2.016 grams per mole, because H2, we need to double that. So now we've got our grams canceled out. I want to turn my hydrogen into ammonia. Turn my hydrogen into ammonia. We're going to do that by putting H2 on the bottom and ammonia on the top. The numbers that need to go in here are the mole ratio coming from the coefficients from the balanced equation. That's a 3 in front of hydrogen and a 2 in front of ammonia. So now hydrogen, top and bottom, cancels out. Boom, boom, there we go. What we have right now are moles of ammonia, but I don't want moles, I want mass of ammonia. So one more step, I have moles on top, put moles on the bottom, turn my moles back into grams. Molar mass of ammonia, NH3, is 1 nitrogen and 3 hydrogens. That is 17.031 grams per mole. When I do this math, I'm going to multiply everything on the top. 12 times 1 times 2 times 17.031. Divide by everything on the bottom, divided by 2, divided by 3. And our final answer is 68.124. We're going to keep 2 sig figs, 1, 2, that 1 is going to turn that 8 into an 8. Unit label, grams of ammonia, is our final answer. All right, so now we're going to do a similar but slightly different problem, looking at volumes and volumes. So STP, remember that at STP we have 22.4 liters per mole of an ideal gas. So here is my given, and here is my wanted. So we always start with our given, 19.8 liters of SO3. Always, always, we need to convert to moles first. I have liters on the top, put liters on the bottom, turn my liters into moles. What do I know about liters and moles? At STP, I know 22.4 liters. 22.4 liters in 1 mole. So now liters, boom, boom, is canceled out. I have moles of SO3. As soon as we have moles, we can use our mole ratios. Have SO3, put SO3 on the bottom. I want to turn SO3 into oxygen, put O2 on the top. We're going to use the coefficients from the balanced equation. This gives us our mole ratio. I have an invisible 1 here in front of oxygen. We have a 2 in front of our SO3, a 2 in front of our SO3. So now it cancels out SO3, top and bottom, boom, boom. What do I have left? I have moles of oxygen. I have moles of oxygen. So close. I want liters of oxygen, not moles of oxygen. So I need to do one more piece in my railroad tracks. I want to get rid of moles, put moles on the bottom, turn my moles into liters, put liters on the top. What do we know about liters and moles? We know that there are still 22.4 liters in 1 mole at STP. Now, calculator-wise, 19.8 times 1 times 1 times 22.4 divided by 22.4 divided by 2 divided by 1. What does that give us? 19.8 times 1 times 1 times 22.4 divided by 22.4 divided by 2 gives us 9.9. Unit label, liters of oxygen. Ooh, because moles got canceled out, I forgot to click that off. 9.9 liters of oxygen gas is our final answer. Good? Good. Go ahead and do this one in the Ed puzzle. Think about your given. Think about your wanted. Start with the given, find the wanted. Remember that you have to convert to moles first before you can use your mole ratios. All right, so given was 9.4 liters of oxygen gas. We want to make that go away. What do we know about liters? There are 22.4 liters in 1 mole of an ideal gas at STP. So I've got liters canceled out. We have moles. As soon as we have moles, we can use our mole ratios. I have O2. I want it to go away. Put O2 on the bottom. I want to flip my O2s into sulfur trioxide. Tri is 3. So SO3. Coefficients, I have a 2 in front of my SO3, invisible 1 in front of my O2. What cancels out now? O2. Gone, gone. We're left with moles of SO3, but I don't want moles of SO3. I want liters of SO3. So I'm going to take those moles, put them on the bottom, flip my moles back into liters. What do I know about moles and liters? I know that there are 22.4 liters in 1 mole. So now I can cancel out moles top and bottom. Gone, gone. And calculator, what are we going to do? 9.4 times 1 times 2 times 22.4 divided by 22.4 divided by 1 divided by 1. That's going to give us 18.8 unit label liters of SO3. Quick sig fig check. I have 2. I have 1, 2, 3. I'm going to use that 8 and round up to a 9. Final answer with sig figs, 19 liters of SO3. So here's another example, but now I'm mixing all the things up. We're going from mass, grams, to volume, liters. So I still have STP, so we're still talking about 22.4 liters per mole at STP. I want to find liters of SO3, so this is my wanted, but my given is in grams, grams of oxygen gas. So we're going to start with our given, 48 grams of oxygen gas. We're going to flip our grams into moles. And once we have moles of oxygen, then we can use our mole ratios, get rid of the oxygen, and turn our oxygen into sulfur trioxide. We're going to use the coefficients from the balanced equation to plug in here. Now we'll have canceled out grams and we'll have canceled out oxygen. I have moles of SO3. I don't want moles of SO3. I want liters of SO3. So I'm going to go ahead and put those moles on the bottom to cancel them out. Turn my moles into liters. Think about how many liters in a mole at STP, how many liters in a mole at STP, and then here this gram number, we're going back to our handy dandy periodic table. How many grams in 1 mole of oxygen gas? Good. Finish this one on your own. So we figured out that there must be 15.999 times 2, 31.998 grams per mole of oxygen gas. Now we can cancel out grams. I want to get rid of oxygen and flip my oxygen into SO3. I can do that because I have moles now. I'm going to use the mole ratio from the balanced equation. 1 oxygen to 2 sulfur trioxides. So here we have successfully canceled out the oxygens. Oxygen gone, gone. But my final answer, I need to find liters of SO3. So I'm going back to how many liters in a mole at STP. We know that there are 22.4 liters in 1 mole at STP. So now I can cancel out moles top and bottom. Moles top and bottom cancel out. I have liters of SO3 left. Liters of SO3 is my wanted. So now with our calculator, we're going to do 48 times 1 times 2 times 22.4 divided by 31.998 divided by 1 divided by 1. And our final answer is going to be 67.2042. So many digits. We're going to keep 1, 2 sig figs. 1, 2 sig figs. That 2 is going to leave. That 7 is 7. Final answer is 67 liters of SO3. So here's a similar question, but again, we're mixing things up. Particles to mass now. Particles like atoms or molecules to mass. Mass is grams. So here, tin 2 fluoride is in toothpaste. Here is the reaction that makes it. Our reaction is not yet balanced, so always make sure that we balance first. So I've got 2 fluorines. I only have 1 fluorine on this side. I'm going to put a 2 here. That's good because I also have 2 H's. And now I have 2 H's. And voila, equation is balanced. So stoichiometry today. How many grams of SnF2, tin 2 fluoride, can be produced by reacting 7.22 times 10 to the 23rd molecules of HF, hydrofluoric acid, with excess tin? So this is my given. This is my wanted. So we always start with the given. 7.22 times 10 to the 23rd molecules of HF. Step 1, we always have to convert to our moles first so that I can use our mole ratios up here. So how do I get rid of molecules and turn my molecules into moles? I put molecules on the bottom and I put moles on the top. What do we know about molecules and moles? We know that the very handsome Avogadro didn't actually tell us, but we named the number after him. There are 6.02 times 10 to the 23rd molecules or atoms or other particles in 1 mole of anything. So now we have canceled out molecules top and bottom. I have moles of hydrofluoric acid, but I don't want moles of hydrofluoric acid. I want tin 2 fluoride. So we're going to get rid of HF by putting it on the bottom. And I'm going to flip my hydrofluoric acid into tin 2 fluoride. And I can do this because I have moles. And so now I have moles, I can use my mole ratios. I have invisible 1 and very visible 2. Good. So now what have we canceled out? HF top and bottom. I have moles of tin 2 fluoride, but I don't want moles, I want grams of tin 2 fluoride. So we're going to extend our railroad tracks just a little bit more. I want to get rid of moles because I have moles on the top, put moles on the bottom, turn my moles into grams. Now what do I need to do? I need to go to my periodic table and find the mass of tin 2 fluoride because I need to know how many grams are in 1 mole of tin 2 fluoride. So tin is here, 118.711. We're going to add 2 times fluorine, 18.998. That gives us a grand total of, calculator says, 118.711 plus 2 times 18.998. 156.707 grams per mole tin 2 fluoride. So here we have successfully canceled out moles top and bottom. Unit label left, I have grams of tin 2 fluoride. This is good because that's exactly what I wanted to find. Back to the calculator. We're going to multiply everything on the top. 7.22 times 10 to the 23rd times 1 times 1 times 156.707. Divide by everything on the bottom, divided by 6.02 times 10 to the 23rd. Since we're dividing in scientific notation, make sure, my friends, that you are either using that EE button or parentheses around the scientific notation so that things get divided correctly. I also need to divide by this 2, so I'm going to also do divided by 2. Finally, final answer, 93.97213. So many digits. How many sig figs do I get to keep? 1, 2, 3. 1, 2, 3 sig figs. So I'm going to keep 1, 2, 3. That 7 is going to pop that 9 up to a 10, which means that my final answer is going to be 94.0. Because if that guy goes up, that guy goes up. 94.0 grams of tin 2 fluoride, SnF2, is our final answer. Guess what? I'm going to have you do this one on your own. So now we're going to kind of reverse it. I want you to figure out how many molecules of hydrogen gas, can we make by reacting 12 grams of tin. So again, balance that equation. We did that on the last slide. That's going to be a 2. Now what? We're going to start with our given 12 grams of tin. You're going to turn those grams into moles. We're going to have moles of tin. Once you have moles of tin, you can use mole ratios and figure out how many moles of hydrogen gas there are. As soon as you have moles, you can use Avogadro's number, the mole number, to figure out how many molecules of hydrogen gas there are. Remember that there are 6.02 times 10 to the 23rd molecules in 1 mole. Good? Go. All right, answers. Are you ready? We threw a 2 in there. We balanced that equation. Done. Start with our given, those 12 grams of tin. We're going to turn our grams into moles. We know that tin is 118.711 grams per mole. Now that I have canceled out our grams and we've got moles of tin, as soon as we have moles, we can use our mole ratio. Tin is going to go on the bottom. I want to get rid of it. I want to turn my tin into hydrogen, put H2 on the top. I have invisible 1 and invisible 1. This is going to make our math super easy. We have 1 and 1. So now we have canceled out tin, top and bottom. We're left with moles of hydrogen, but I don't want moles of hydrogen. I want molecules of hydrogen. So I'm going to take that mole, put those moles on the bottom, turn my moles into molecules. What do we know about molecules and moles? We know that there are 6.02 times 10 to the 23rd molecules in 1 mole. So now we have successfully canceled out moles top and bottom. We are left with molecules of H2, which is exactly what we're trying to find. Back to the handy dandy calculator. 12. And this time I'm going to go step by step. So I'm going to do 12 times 1 divided by 118.711 times 1 divided by 1 times 6.02 times 10 to the 23rd divided by 1. We're going to get the same answer. Sometimes it's just fun to switch things up a little bit, right? So 12 divided by 118.711 times 1 divided by 1 times 6.02 times 10 to the 23rd divided by 1 gives us a grand total of 6.085536, lots of digits, E22. What does this even mean? Well, E22 means times 10 to the 22nd power. How many sig figs do I get to keep? I get to keep 2. 1, 2. That 8 is going to turn that 0 into a 1. Final answer, 6.1 times 10 to the 22. What's my unit label? Moles is gone and tin is gone and grams is gone. So all we have left are molecules of hydrogen gas, H2. Final answer. We did it! So my friends, we defined stoichiometry is just the math of the recipes of chemistry. We talked about all the stuff that we can find from balanced equations. The most important one that we talked about today were mole ratios. Then we use those mole ratios to do lots of stoichiometric calculations. The goal, or rather the most important thing to remember, is you've always got to convert to moles first before you can use those mole ratios, because they are mole ratios, not gram ratios or liter ratios. Good. You did it. Well done.